Welcome to physics lesson 8.5. Simple machines. Get to the chopper. All right. So simple machines. The idea of any machine is to make your life easier. So we measure this in something called mechanical advantage, and this is the ratio of force that you need to put in versus how much the machine puts out. So FR here is your resistance, also known as your load force. Fe, that's your effort, also known as U. So that's how much you put in, this is how much the machine puts out. And it's all known as MA, or mechanical advantage. Alright, so as far as machines go, they increase force, they do not increase energy. So ideally, the work output should be the work input, because work is change in energy. So the change that you get only can equal what you put in. It's not going to increase energy, it's only going to increase the amount of force. So you can never have more work coming out than you are getting put in. That being said, you can have more force, or you can have more distance. All fun things. So that brings us to something called ideal mechanical advantage, which deals with, you guessed it, distance. So what we can have is the distance you have to put something in over the distance out. And this could be delta y as easily as it is delta x if it's moving up. And that's called IMA. Ideal mechanical advantage. Don't finish that sentence. I'm watching you. Alright. Now, in a perfect world, work input equals work output, but unfortunately we lose a little bit to the environment and the efficiency. So you put more work in than what you get out. Efficiency is kind of like the grade of a machine. So if a machine is 100%, that means it's 100% efficient. Everything that you put in is what you're getting out. Most machines are not 100% efficient. So the higher the efficiency, the better the machine. There's two ways that you can measure efficiency. Both are exactly the same as far as efficiency ratings go. One is the work output divided by the work input, multiply that by 100. Efficiency is a percentage. It is not a set value. So there won't be any units. The other way we can do that is take the mechanical advantage. So remember the force output versus input ratio, and divide that by your ideal mechanical advantage, which is going to be your distance ratio, and then multiply that by 100. Alright, so practice problem. This one is going to be a little bit lengthy. I'll try to do it as efficiently as possible. Little physics pun there. Okie dokie. Artichoke. You exert a force on a lever. So here is our lever. You're exerting a force of 225 newtons. And the idea is to move this 1,250 Newton rock a distance upwards. I want to draw this that way. 0.13 meters. The efficiency of the lever itself is 88.7. How far do you need to move your lever? So a couple things here. First, we're going to need mechanical advantage. So this is force out divided by force in. Then we're going to need ideal mechanical advantage. Yay! So this one is going to be our distance in over our distance out. How fun. And finally, it mentions efficiency, so we're probably going to have to deal with our efficiency, and that should equal either our work ratio or mechanical advantage over ideal mechanical advantage times 100. Alright, let's start with the red one first. Mechanical advantage. Force output, we need to raise 1250 over the 225 that we need to put in. That should give us 5.56 with no units. It's a ratio, so the units of newtons would divide out. So we're set there. That one is set. Ideal mechanical advantage. So we want to know our xi. We want to know the distance we have to push this lever in order to raise the other side, 0.13. We don't know that. We also don't know what the ideal mechanical advantage is. The only thing we do know is it needs to go up 0.13 meters. So that means we need to either figure out xi or IMA. The last one, our efficiency, that should equal 5.56 over IMA times 100. And our efficiency is given to us at 88.7. That means we can solve for ideal mechanical advantage and then place it over here. Yay, how fun. Alright, so let's go ahead and do that. 88.7 equals 5.56 IMA times 100. Alright, let's get rid of that 100 first. So we're going to divide each side by 100. 100 will cancel out here. 0.887 equals 5.56 divided by ideal mechanical advantage. I'm trying to avoid saying IMA because it sounds like I'm going to say something silly, and I never say anything silly. So how dare you think I would say something silly? Alright, next thing, multiply ideal mechanical advantage on each side, cancel out here. Ideal mechanical advantage over here. So 0.887 ideal mechanical advantage equals 5.56. Divide each side by 0.887. 0.887 cancels out here. Ideal mechanical advantage should equal 6.27. Alright, now that we have ideal mechanical advantage, we can plug it back over here into our green equation as 6.27. That should equal the distance we need to push that lever down over the distance the other side is going to go up. Multiply each side by 0.13. And we're left with xi equals 0.81 meters. So we need to push this down 0.81 meters in order for that to go up 0.13 meters. Alright, so let's talk about a couple simple machines real fast. I know this is another longer one. I'll try to keep it under 10 minutes if possible. No promises. Alright, so there's 6 basic types, and they all relate back to the ideal mechanical advantage. So the lever is what we just did. We have a wheel and axle. That relates to ideal mechanical advantage to the radiuses of the wheel and the axle. And then we have the pulleys. The pulleys relates to how many pulleys you have. So the more pulleys, the larger ideal mechanical advantage is. So 1, 2, 4. More pulleys equals the ideal mechanical advantage. You just add them up. Inclined plane, depending on the height. Wedge, same idea. And then there's the screw, which depends on the width of the threads and the diameter of the screw. Um, okay, so let's call it there, and I'm going to draw a smiley face, maybe give it some hair. That's cool. And maybe a little goatee, because, I don't know, that sounds fun. Alright, talk to you later. Hasta luego.